Okay, welcome everyone to this webinar on enabling the next generation of long-range current profilers. My name is Jan Overly and I'm today's moderator, and our speaker today is Nortek founder Avle Lorman. The presentation today will last 25 minutes and we'll gladly take your questions. You can at any time press the raise hand button at the top of your screen and we will unmute you. If you find it easier, you may also enter your questions in the questions from the audience window, which we will be putting up. If there are many questions, we may stay on past the 30 minutes. And we hope that you take the time to answer our short survey, which will pop up at the end. I'm pleased to hand you over to today's speaker. He is the founder and chief technology officer here at Nortek, and he has been working on acoustic Doppler technology since 1989. We've got an exciting webinar in store for you today, and we're here to talk about how Nortek has employed AD2CP technology to push current measurements as far as 1,000 meters. So, to talk about the new Signature 55, which you can also see in the back here, and how Nortek is enabling the next generation of the long-range current profilers, I give you Avle Lorman.
Thank you very much. Yeah, today we're going to talk about long-range instruments, and there is a long story, obviously, behind every type of development, but in this particular case, we're going to start with going back a couple of years when we were wondering what it would require to really make a long-range system. And it is indeed fairly complicated. There's a lot to it, other than the fact that you have to make instruments that you can no longer carry around under your arm. There were things like the electronics to drive it, the transducer element, which is maybe was the most worrisome aspect of making something like this. These things are big, heavy, and they behave very differently than smaller transducers do. You have things like interfacing requirements, mechanical design, which was a challenge that we didn't really know at the beginning how we were going to handle. And of course, there was the signal processing, which comes along with the development of the new 82CP generation of products that we've been working on for at least now 2.5, 3 years. Which is the first really truly broadband processing electronics that we have developed at Nortek, and evolving that into something that really worked was quite a challenge for us and took some time. Having said that, there is probably nowhere where broadband processing is more useful than in long-range systems. So there's a consistency between the processing requirements and the long-range systems that we're applying them to. So if you take these things one by one, the 82CP electronics was developed initially for the collaboration we did with iRobot for the Sea Glider, and it was finished or actually released as part of the glider electronics in the summer of 2012. You see a small photograph of it here on the PowerPoint. It's a two-processor design. It's got two DSPs in there in addition to a huge FPGA that controls all the timing parameters. One processor is doing all the broadband processing for the actual velocity, and the other one is an interface processor. So it really is the one that handles the Ethernet interface that all of these 82CP systems come with, which is kind of an exciting feature, and more we work on it, the more we see the benefits of having swapped interface system. There is, of course, also specific components on here, not so much because of the frequency, but because of the power requirements of a 55 kilohertz system. We're outputting a lot more power than we are in our shallow systems, and that means that the transmit section had to be redesigned. So the boards that actually go into the 55 look a little different than this image. They're a little larger, and they have more power components on them. And an important aspect of this is that power consumption has now become equal to the transmit power. So there really is the time when you're sitting there spending a lot of time power when you're really not doing anything, that era is past and beyond us. So today you can pretty much estimate that whatever you're going to be spending in power is whatever range and the number of pings and things like that that you're going to get. So it's all about basically managing the transmit power. So the transducers was probably the scariest part for us. It has to be broadband. We really need good transducers in order to get good range. It's really a big item as an individual piece or component. So you have these huge blocks, and in our case, they measure something like 25 centimeters in diameter. So you can't make this stuff out of one disk. You have to do something more. And we were lucky enough that we were able to take advantage of the acquisition of a small company in Aberdeen, which was called PCT at the time, and then later on became Nortek Piezo, which is basically a dedicated production facility that makes piezo composite transducers. And this allows us to take smaller blocks of transducers or transducer elements and put them together into larger disks. It also allows us to remove a lot of the material that's being used in the ceramic, so that even if it is very large, it's still quite light compared to what a solid ceramic is, because you're removing a significant portion of the material in the process of making these things. So you get the broadband and you get lighter transducers sort of almost for free. Now, I say free, but they're obviously not. They're kind of expensive. So it's not something you would want to use for a smaller transducer, but for our particular purpose, it was very valuable. So why did we make them so large? I mean, what's the big deal about making large transducers? So these are about 25 centimeters in diameter, and the current systems that are out there operating at 75 kilohertz are about 15 centimeters in diameter. So I think there are really two things that we think about. One is the improved range. We get about 4.5 dB improved SNR because the increased directivity that comes along with having a large transducer, which is very nice. And the other part of it is that it has a smaller opening angle. So that means that when you mount something like this on a structure where you may have interference from things that are mounted in the vicinity of the system, you have a little more suppression of the energy coming back. That is true at least when it's operating at 75 kilohertz. When you operate the system at 55, and this really is a dual frequency system, when you operate at 55, the larger transducer is really partially just recapturing the size that, in a way, we lose because we're at the lower frequency. So the beam width, effective beam width, obviously becomes larger again when you go down to 55. And they're actually about the same as the current 75s that are out there in the market. So there's some numbers that worked out that way. But as from the get-go, the improved SNR and the improved or smaller opening angles were the two main factors and reasons for making these into large transducers. Now, in terms of bandwidth, the effect of the composite transducers is that you, in addition to have the intrinsic bandwidth that you get from a composite scheme, you can also add more bandwidth by actually putting on matching materials. And these transducers are both composite and matched. So they have a very wide band. They're actually around 50–60%. And that allowed us, and there's a long story behind this, but in the end, it all comes down to the fact that we can really operate the same transducer in two different bands. So what we have done with the signature 755 is that we operate in different portions of the spectrum of the transducer depending on the preference. So if you would like to have short range and high resolution, you work at 75 kilohertz, and that is has about 18 kilohertz bandwidth, which corresponds to about 25%. If you want the optimum range, you work at 55 kilohertz and you use a narrow band approach to it. So you're only using 3.5 kilohertz of bandwidth, which comes down to about a quarter of 25, which is 6.25%. So this way, you can actually alternate between the two modes during deployment. And this is kind of a new feature. So you don't have to configure the instruments to work at one way or the other and determine that before you start. You can actually alternate during the deployment between the two modes. So you can look for optimum range, mean currents, and then every so often, if you wish, you can look at things like internal waves with a little shorter range system. And then you can have higher spatial resolution and higher time resolution if you want to, because the larger bandwidth and shorter range allows us to ping faster and to do so with more precision. Precision is related to the broadband processing, which is a little different than what it has been in the past. Whereas most systems out there today use various forms for phase coding, the Signature 55 actually, it's got a frequency-based coding scheme on it. That means that we change the frequency as we transmit. And this is very often referred to as a chirp, because the sound, and I'm not going to try to sing today, the sound is very similar to what a bird would make. So you have this change in frequency, rapid change interface with little chirps. So this coding scheme, which is really what it is often referred to as a chirp. It it has some advantages compared to face coding. It does allow us a little more freedom in terms of defining the transmit sequences. And we have seen in the data that at low SNR it has very little bias, and this is a very good thing and fairly important thing when you make instruments, because it means that at the very end of the profile, when you're out there almost at 1,000 meters, there's very little effect on the velocity. So you're able to measure the velocity accurately all the way to the very end of the profile. Bunch of new features in these systems. We talked about it initially. As a user, you have full control over the transmit power, and thus you have full control over the power consumption. So because of this tight coupling between the two, you basically can control this instrument exactly the way you want in terms of the power consumption and available battery power that you have. You can alternate the data collection modes. We talked about it a little bit. Switch between long range, low resolution, and short range and high resolution. We do, and I must admit, we stole this idea from someone else, and I'm not really ashamed about it because it's a good idea. We store all the data that we collect. So if you are collecting 30 samples or 30 current profiles, and you're normally averaging all of those to form one mean current profile, in this particular case, with the system, we now store all the individual profiles, and then we can do QA, QC on the data afterwards and allow us to remove things like interference, fish, and things you really do not want to have in your data. And this I think, is a fairly important step forward towards a more consistent quality in the data. Nice trick. Smarter interface, Ethernet interface, long story again. Serial ports gone from the computers. We're all now using serial to USB converters. Kind of a mess. We made a leap this time and said, let's put a true Ethernet interface into this. So you can actually now use your network cable and connect to it. And not only that, you can sit in your office and have the instrument connected to a switch out in the lab, and you don't have to go anywhere. You can actually continue to sit in your office and talk to the instruments, test different configurations. You can set it up for tests. You can do all kinds of different things from the warmth of your office instead of having to go out there. It also has a lot of consequences for instruments because you can have more than one instrument on the same switch. You can have things being time synchronized, etc., etc., etc. Some interesting concept there. Telemetry file is a special file structure that basically is a subset of all the data that we collect, so that if you are interested in transmitting over a low bandwidth link like Iridium or an acoustic modem, subsets of the data, you can use that using this telemetry file concept. And of course, for all of those who have been waiting and waiting for data to be transferred over the serial line, there's now an FTP protocol that allows you to do 20 megabit of transfer, which means that a gigabyte file comes into your computer in about 6 minutes. Big change, especially when you're out on the ship and you don't have a lot of time. And so it's a very nice feature, and it's become very popular by those who have started using the 82CP platform. Last one. Compass calibration in these large instruments can be difficult. It may be required when you're changing batteries, and if there is a potential influence from the magnetic part of the alkaline batteries onto your compass, or if there is material in your rig that can affect the compass. So what we do now is that we collect all the raw magnetometry data that is being collected during the deployment, and if you're on a rotating deployment, as you are on most mooring structures, you will have a lot of data that you can basically use to post-calibrate the compass when you come home and correct for any heading error. And I think this is a very effective way of generating better quality directional information data, which obviously is important for a lot of the larger ocean currents, where small changes in directions are very relevant. So removing local magnetic fields, and the spinning portion of this operation that you normally do in the lab, you actually now sort of simulate when you're deployed, assuming, of course, again, that the instrument is spinning. This particular plot you see here is from an instrument that has been spinning about half a circle. So it's been moving back and forth around 180 degrees during the deployment. But this is enough. You don't have to go all the way 360. This is enough to actually check or correct the compass and get an improved directional estimate for your current data. So into the testing part, a lot of testing, has been going on. Started in December 2012, going through a lot of work was done on the matching between the transducers and the electronics. We learned a few things there that we didn't really know about since we hadn't really worked on the long range systems before. Up to 2 beams in April 2013. We got down to 3 beams in June 2013. So the first oceans test came up in 2013. But before that, we were kind of puzzled by the question about how we were going to evaluate the performance of these systems. Because the reality is that depending on the combination of scatterers, or what kind of scatterers that we have in the water, we basically have a situation where if the scattering is really weak, we can have a range that's much shorter than the range that we will have if the scattering is very low or strong. So it sort of is a game here where the variability in the ocean really renders all tests or all objective tests very, very difficult to conduct. So what we did was that we basically simulated the loss curves, and we looked at this, and we said that if, in one situation we can have, or in 2 different situations with different scattering material, we can have range variability from 370 meters, in this case, up to 500 meters. So how are we going to say this is a good system or a bad system, or is it better than this one, or is it better than yesterday, or how are we going to do this? And we really agreed amongst ourselves that the only way to do this was to compare with someone else. So we sort of did what we had to do, and we went down to an area with deep water, and we hung one of these long rangers on there. It's a 75 kilohertz instrument, and then we took the signature. At that time, it operated at 60 and 75, and hung it next to it, and basically compared data as apples and oranges as we possibly could. Same kind of power levels, same bandwidth, same cell sizes. We tried to match everything best as we possibly could, and then really tried to say something about how did these 2 systems compare. And there's a lot of data collected. I'm not going to show it all to you. This is one sample where we have 3 curves. One is the workhorse, which was a reference instrument here, which was operating at narrowband, or in low power mode in narrowband. The other curve here is in high power narrowband. And then there's a signature operating, I think, at 61 or 62 kilohertz at that point. And these 3 curves are now sort of plotted on the same curve relative to the individual noise levels in the different systems. So you basically have a dB referenced to a noise level on the vertical axis, and on the horizontal axis you have the range. And in this particular case, the ship that we were on was about 1,100 meters above the seafloor. So the bump that we see at the very end of the range is the seabed. The signature 60 in this particular case got about 916 meters. The workhorse at high power got about 728. The low power version of the same thing got about 588. Again, this thing about the scattering, if you look at the data collected around 220, 230 meters, you see there's almost like a hole in the scattering. And actually, when the workhorse was operating in low power and broadband mode, we didn't even get data in that particular hole. So around 220 meters here was nothing. So what came out of that, or how do we do this, or what kind of conclusions could we draw? Well, we mentioned that it can operate at 2 different frequencies. Those frequencies have been changing around a little bit. Right now they are at 55 and 75. At that point it was about 60 and 75. So when we were operating at 75 kilohertz, we got about the same range as the RDI at this particular case, nominally about 600 meters, which is RDI spec for the 75 narrowband high power. But we generally spend less power than they do. When we tried at 62 kilohertz, we nominally got 200 meters more range than the 75. So we got about 800 meters. So that's how we referenced it. Basically, we saw how many more meters do we get? How close are we? We basically use that as a reference, and then we use RDI specs as a reference. May seem a little strange, but it's the only way we found to deal with this, because there really is a huge variation in the scattering in the ocean, and there is no absolute comparison unless you actually want to go to the point of running absolute calibration on these systems, and nobody is doing that today. So out of this, we said, okay, this is sort of tempting. If we have the bandwidth to go all the way down to 55, well, if we do that and we do all the math correctly, we have the potential of getting 1,000 meters in these same conditions. So instead of getting 600 meters, which is sort of the longest range, basically, if they could get 600, we can get 1,000 if we operate with the system at 55. So that's what we decided what to do. And when we had made that decision, we kind of looked like this. It was a happy day, and so now there was just a little bit of work left, and then we could move on. So in the fall of 2013, we spent a lot of time trying to shift the frequencies around. We changed the transducers a little bit, we changed the electronics a little bit, and then we had the first self-contained deployment of the system operating now at 55 kilohertz in February of 2014. So it took a little bit of time, but then again, a lot of other things were sort of put together at the same time. So this is a small boat with the Signature 55 and actually deployed from a rib. I thought that was kind of impressive, given that it's deployed at 1,260 meters. So you can sort of see there the photograph of the transducers, the yellow ones. And then right behind there, you can see a little frame structure, a cable, and there's a battery canister below there. So this is a single alkaline battery pack that this thing was run on for about 8 or 9 days. We deployed it at the same site as the initial range test, so we could kind of reference a little bit of what was going on. 1 week, about eight days actually. And then we alternated between 55 kilohertz 20 meter range cells with full power and 75 kilohertz and 5 meter cells with about a quarter of full power, which is quite a bit less in terms of battery consumption. So this is the data. This is the range data. So 2 curves here, a blue one, which is the signal to noise ratio. You can still see these sort of things going up and down. The green line is the correlation values, which in this particular case drops as you get down to the end of the range. So the horizontal axis is going from 0 to 1,400 meters. Surface is around 1,200 and something. And if we use a commonly accepted threshold for the range, which is when the correlation drops to about 50% of its initial value, we got about 1,020 meters. So this is 55 kilohertz, 20 meter, full power, 1,020 meter range. And we do that actually despite the fact that there isn't a lot of scattering close to the surface. It's kind of interesting to see. If the scattering level that is down at about 100 meters had extended all the way to the surface, we would have gotten quite a bit more. But that doesn't really matter. I think we're kind of happy to just get the 1,000 meters. So yeah, I think we got on the PowerPoint here, we got about the same comments. This is operating at 75 kilohertz. And now we're doing a quarter of the power broadband, and it's 5 meters and range cell. And it's the same site, and we're just alternating. It's part of the data collection of the first week. I think we ran this for about 6 hours or so, just to sort of have a test go at it. SNR curve, you can see that, and then the correlation again drops down to 50%. Now it drops down at 620 meters. So at 75 kilohertz in broadband mode with 5 meter resolution, we actually got 620 meters. We attribute that partially to a good system, but we also attribute it to a high signal noise ratio in this particular area. So we're not claiming that we're going to get that everywhere, but at least this is an indication that it is working quite well and is doing what we expected it to do, which was to get about 600 meters when the narrowband 55 would get about 1,000 meters. So this is full bandwidth. This is 25%, range of 620 meters, and this is the average data. So finally, we took the velocity data, should show some of those as well. The system display, or the display shows the north-south velocity components from the 14th of February to the 20th of February, so it's about six and a half days. The color coding is such that red means northward velocity and blue means southward velocity. The depth curve on the vertical axis goes in from 1,240 meters up to the end of the range, which was 1,020 meters. So here is close to 200 meters, 240 meters or something like that below the surface. We have average data over 30 samples. This was all raw data being collected. So the 30 samples in this mode brought us onto a standard deviation, which was below 1 centimeter per second. The 30 samples we collected over about 3 minutes, and it kind of works nicely. The next test that's going to be done, which is being done actually as we speak, I think, is a range test outside Sri Lanka. We're looking to see what kind of range we're going to get in other types of environments. Because obviously, since the scattering varies across the globe, it would be interesting to see what some other places are giving us. I think there's also a planned test for now in April in offshore South Africa. It's coming up, and it's also got the same purpose to see how close or how much more or whatever, how the actual data performance relates to the 1,000-meter specification that we now have. So I think with that, it's, I think we'll conclude this and take any questions if there are any. Thank you.
Okay, thank you very much there, Atle. We are putting up the questions from the audience window, where you can type in your questions. You may also vocalize your questions if you want. You can use the raise hand function. Press the raise hand symbol at the top of your screen. And also make sure to press the white microphone symbol to activate your audio. But also, as I say, you can also type in your questions in the questions from the audience window. While we wait, Atle, I was meaning to ask you, how surprised were you with these results?
Well, I think I'm not a fishery biologist, but I think one of the interesting things was sort of to see how the scattering conditions in the oceans were much stronger than I ever thought. Mm-hmm. I almost expected there to be very low scattering as we came down there, and there is I don't know what the fisher biologists I'm really an amateur in this area, but there's a much more stuff in the ocean than I thought, and the consequence of that is that we do get a lot more range than I thought we were going to get.
When you say stuff, what kind of
yeah
materials would that be?
Well, I keep asking all the marine biologists I run into what is down there. Because especially there was a very large abundance between about 1,100 meters depth and up to about 800 meters. There was a lot of material there. And some people say they're little fish, like 2 or 3 centimeter long fish. Some people think they are squid. Some people think they are some form of jellyfish. So I don't know. I mean, maybe we should mount the camera on this thing and put it down the next time.
So there's always going to be conditions and challenges wherever you go.
Well, there's going to be different types of stuff in different places. And I think the people who have worked in the offshore community have told me that they get very different range results if they go offshore Angola. Brazil is another area, Gulf of Mexico. But I think just in general, it looks to me like there is. I'm less worried about the range now than I was when we started.
Yeah. Okay, thank you. Any questions out there? We are happy to answer them. See, getting it up now. Okay, we got one question from Bruce Magnell. How does power consumption at 55 kilohertz high power compare with the LR75?
I think we are spending about 400 watts. So hang on a second. Let me think a little bit. It's actually very close. I think the full blast mode, because I think that nominally the workhorse with 4 transducers spends about 250 watts per transducer, and I think we're very close to that. So in terms of the total power consumption, I think the high power mode and the workhorse is going to be very similar to our full power, either whether it's a 75 or a 55. Okay. Yes, but at 75 we would get, because of the larger transducers, we would then comparably get more range. So what normally people would do is, if you want to operate it as a 75, you pull down the power a little bit, and then you would get roughly 4 times the deployment period or deployment time that you would with the long range in high power mode today, if you're running both at 75. If you get it at 55, you would have to really, you're going to have to pull down a little bit how often you're going to collect data if you want to have like a 1-year deployment, for example. You cannot get that every 10 minutes, for instance, at 55. So to be quite honest, the 55 kilohertz long range mode with full power was intended primarily to be something that was used on the platform thing where you have external power.
thanks. Hope that answers your question, Bruce. Thank you for that. Looks like we have no more questions. Let's see. Okay, Alan, any final comments?
No, I don't really have any. It's a good system. It's doing what we're expecting it to do, and we got a new system coming. We got one coming up now next week. We're right now we're in the mode where we're testing all kinds of different configurations and setups and things like that. And so we'll keep you all posted about what's happening. And as I said, I think it's really coming around.
Okay, great. Well, it looks like we have no more questions. This has actually been the final webinar in this round of the Nortek Speaker Series. We hope you have enjoyed this and other talks that we have arranged. If you have missed out on some of them, fear not. We have made them all available on Nortek's YouTube channel. And we will be back with another round of the Nortek Speaker Series, won't we, Adley?
Absolutely.
So to get updates on that and coming events and other news, please sign up for Nortek's newsletter, like us on Facebook for news, events, and also pictures of Nortek deployments from all over the world. So we thank you so much for joining us and hope to see you all again soon. Until next time, this is Atle and Jan in Oslo signing off. Thank you and goodbye.